Hello and welcome to the first part on Unit 15. Unit 15 covers fluids and we will have three parts here. The first part here is going to cover pressure. And we're going to start by looking at states of matter. So typically there are three states of matter. Yes, I acknowledge that fourth would be plasma, but we're just going to deal with solid, liquid, and gases here. So a solid is a state of matter where it has a definite defined shape and a definite defined volume. Okay. The liquid phase doesn't have the defined shape. It takes the shape of whatever container that it happens to be in, but it does have a fixed volume, right? I could take the same amount of liquid and pour it into another container and it would be the same volume. And then lastly, we have gases, and gases are kind of directly the opposite of solids. They take the shape of whatever container they are, and their volume is determined by the container. There's also differences in the molecules for these three. Solid has the molecules and the atoms fairly tightly packed together. Liquids, they're freer, and gases, they have are much smaller bonds, would be a good way of saying it. Okay, so now this unit is on fluids. Fluids are liquids or gases. Plasma would be a fluid as well, but for our purposes primarily we're going to look at liquids and gases, not glasses. Okay, so moving on. Question for you. So what's different about walking in the snow with snowshoes versus not? Right? Okay, so what stays the same? So things that stay the same is your mass, your weight, right? Particularly if you consider the two with the snowshoes strapped to your back, so you're not losing that amount of weight when we change places here, right? But the thing that really changes is the size of your foot. And I didn't keep with my same format, but you get the idea, right? Mass stays the same, the size of your foot changes. So what that really adjusts is how much pressure you're putting down. So pressure, by definition, is a force divided by an area. You can see from the definition that the units are going to be something like Newton meter squared. But as we've seen a lot of times, Newton meter squared has a named unit, and this would be the Pascal, in honor of Pascal, who did a lot of work with pressure. So we're going to move into an example now, and it's actually two examples. The first example, I guess there's three, looking at my notes. There's three examples. The first one involves an elephant. Okay, so a large elephant, and this is pretty much as big as they come, has a mass of 7,000 kilograms. If you look at an elephant's foot, it's not perfectly circular, but we're going to assume that it is, and that its diameter is 50 centimeters, and that when an elephant is standing, 1/4 of its weight is supported by each foot. So what's the downward pressure from one elephant's foot? Okay, so we know pressure is force divided by area. We can find the force by thinking about what's the elephant's weight. Well, it's its mass multiplied by the acceleration to gravity. So that's 7,000 kilograms times 9.8 meters per second squared. So this very large elephant has a weight of 68,600 newtons. Okay, but 1 foot only takes 1/4 of the weight. So the force for a foot is going to be the weight divided by 4. And if you divide that out, you get 17,150 newtons. Okay. Now we're going to assume that the elephant's foot is a circle. Area of a circle is pi r squared. We're given up here the diameter of the circle. We need the radius, so I'm going to change units from centimeters to meters. I'm going to divide by 2, and I'm going to square all of that. And the reason I'm dividing by 2 is to get from diameter to radius. And if you do this math out, you get 0.196 meters squared. And now we can plug these numbers in. 17,150 newtons divided by 0.196 meters squared. And that works out to be 87,344 and change Newton meters squared or pascals. Okay, so now we're going to basically do the same calculation, but for a human woman. Mass of our woman is 60 kilograms. This is a larger woman. And we're assuming she's in stilettos. Nice stiletto heels. And again, we're going to assume the stiletto is a perfect circle, and we're going to assume it has a 1 centimeter diameter, and that each of her feet supports 1/2 of her weight, and all of that is on the stiletto. Okay, so what's the downward pressure from each foot? So same idea. Pressure is force per area. We're going to start by finding our woman's weight. So 60 kilograms times 9.8 meters per second squared. And that works out to be, forgive my notes, I worked with a different math, so I have to redo the math here. This works out to be 588 newtons. But again, the force is going to be the weight divided by 2 because we're assuming that her weight is equally distributed between her 2 feet. So 588 we divide by 2 and we get 294 newtons. And area again is pi r squared. Oh, not pi divided by r squared. Let's try again. Pi r squared. There we go. Pi, the radius is going to be 1/2 of 1 centimeter, so that'd be 0.01 divided by 2 squared, which works out to be 7.85 times 10 to the minus 5 meters squared. And now we can plug in. We have a force of 294 newtons, and we're going to divide by our 7.85 times 10 to the minus 5 meters squared. 5 times 10 to the minus 5. And we get a pressure here of 3,745,222 Newton per meter squared. Okay, now think about this for just a moment. Okay. Elephant, 7,000 kilogram elephant puts a downward pressure of 87,000 Newton per meter squared, whereas our woman and her stiletto is pushing 4 million, right? That's why stilettos have a habit of breaking through surfaces, because the downward pressure on them is so high. Like if you're walking on styrofoam, stiletto's going to go right through, whereas a regular shoe might not, because the stiletto's all confined to a very, very small area. Okay, moving on. One last topic here, and then the example that goes with it. So as you go down through a fluid, pressure increases. Okay, so here I have a fluid. We can see it's a depth of h above from the surface. The surface area is A, and we can define the volume as the area times the height. Okay. So remember, pressure is a force divided by an area. But that force in this case is going to be the gravitational force of all this water acting above it, or whatever the fluid happens to be. Okay. Now, I'm going to take the definition of density, which is mass divided by volume, and solve for the mass. Mass will be density times volume, but because volume is area times height, I can plug that in. So mass can be written as density times area times height. I'm going to plug that in up here. Density times area times height times the acceleration to gravity, all divided by area. Area cancels. So the pressure variation as a function of the depth of your fluid is the density times the height times the acceleration due to gravity. This is often written as rho GH as opposed to the order I had above. Okay. So let's do an example. What is the pressure if you go down 10 meters in fresh water? So pressure is going to be rho GH. Density of water, remember from our last unit, depending on the units, is 1,000 kilogram per meter cubed. Gravitational acceleration is 9.8 meters per second squared. And our depth here is 10 meters. And if you multiply that all out, it works out to be 98,000 newtons per meter squared, or pascals, of pressure when you go down that far. Now, that seems like a lot, and I'm not going to disagree that it is a good bit, but what you really need is a contrast. Okay, atmospheric pressure. So what pressure do I have on me sitting here at the surface of the earth due to all the air that is above me, right? Atmospheric pressure is 101,325 newtons per meter squared, or pascals. Remember, that's the unit there as well. So when you go down 10 meters, yes, you go up in pressure. You've almost doubled the pressure that is on you. Almost, by going down 10 meters. Okay, that concludes unit 14, part 1. 15, part 1? Whatever this unit is, part 1.